integration by parts. So our objective today is to find an antiderivative using integration by parts. Now, we have learned a whole bunch of different ways to integrate things. We have a table of integrals, we have all these different things, but we have not learned how to undo the product rule yet. And the product rule is one of the first rules that we learned how to take a derivative. So let's refresh our memory real quick as to what the product rule is. And so the product rule is if we have some function, let's say f of x, times another function, let's say g of x, if I wanted to find the derivative of this, so here's our derivative operator, what I would do is I would take the derivative of our first function, f, multiply it by the second function, and I would add that to the first function times the derivative of the second function. And oftentimes in class, we made our life a little bit easier by saying that first function is u, second function is v. And then when we applied that derivative operator, what we did was we took the derivative of u and multiplied it by v plus u times the derivative of v. So you saw this rule both ways with the f of x and g of x and with the u and the v. So whatever way is easier for you, that's how we can work out this problem. So what we want to do now is we want to undo that product rule. So let's undo this. So in order to undo it, we need to undo the derivative operator. And the operator that undoes the derivative operator is the integral. And so if I take the integral of the derivative of f of x, g of x, I get f of x, g of x. I get f of x times g of x. Or if we like the UVs, I get u times v. Now I have to apply that inverse operation, and so then I'm going to get the integral of f prime of x times g of x plus the integral of f of x, oops, I forgot to close that parenthesis, g of x. Or speaking in terms of u and v, I'd have the integral of u prime times v plus the integral of u times v prime. Same thing, written two different ways, whatever way is easier for you. Okay, so now what we want is we really want to have this piece alone, because we're going to want to find the integral of two things that are multiplied together. That's what the point of this is to find an antiderivative using integration by parts. So we want to find an antiderivative of two things that are multiplied together. And so I could rewrite this by subtracting this piece from both sides, from here and then from here, or subtracting this piece from here and from here. And so what that is going to look like is I'm gonna move this piece first, and I'm gonna say that I have the integral, or I'm looking for the integral of f of x times g prime of x. And what that is going to equal is going to be this business minus this business. So f of x times g of x minus the integral of f prime of x times g of x. And really there should be a dx every time we integrate something, right? So there should be dx's added to these. Okay, so writing that in terms of u and v, we would try to get this by itself. And so our formula would be the integral of u v prime equals, oh, that's supposed to be a u. I was just going to do an f. U times v minus the integral of u prime v. So what we just did was we derived this formula for integration by parts. Integration by parts. So you can either use this or you can use this. They mean exactly the same thing. So that's our formula that we're going to use. And we will apply this formula when we have one function times another function. Now, the tricky part of this is we have to figure out which one do we want to be f of x and which one do we want to be g of x. And there are some guidelines for that. So there's some guidelines to make that a little bit easier. I'm going to type them out because I'm not super great at writing with my pen yet. So the guidelines for integration by parts. And let's move this down so we can actually see it. Oops, I'm just moving my whole screen here. So guidelines for integration by parts. First, try letting dv be the most complicated portion of the integrand that fits the basic integration rule. Then u will be the remaining factor. So this is saying let dv be the more complicated one, and then when you integrate it, because dv you're going to want to integrate, so you want that one to be the more complicated one so that when you integrate it, it gets simpler, I guess. Second guideline is try letting u be the portion of the integrand whose derivative is a function simpler than u. Then dv will be the remaining factor. So, sorry guys. So the second guideline is try letting u be the portion of the integrand whose derivative is a function simpler than u. That's the guideline I normally go for. I normally go for let me find u so that when I take its derivative, it's going to be more simple. All right, so those are our guidelines. Let's try an example here and see if we can apply this rule. So let's call this example 1. And we want to find the integral of x e to the x dx. And I like using u and v. It's just less writing for me. So I'm going to use u and v instead of the f of x and g of x. And so we need to figure out which of these is u and which one is v prime. And now what these guidelines are saying is either try letting dv, so the derivative of v, so this one here, v prime, be the most complicated portion of the integrand that fits the basic integral rule, and then u will be the remaining, or try letting u be the portion of the integrand whose derivative is a function that's simpler than u. And so when I look at this here, by assigning x to be u, the derivative of that is a heck of a lot simpler. So if I were to say that u is x, that means du is just dx, because the derivative of x is 1. That is simpler. So I'm gonna assign my u to be the one when I take the derivative. It's simpler. Now, then I need my dv. And my dv has to be the remaining portion of it, which is this e to the x dx. And the antiderivative of e to the x dx is e to the x. So the first one is saying, pick the dv that's going to be easier for you to integrate. The second one is saying, pick the u that's going to give you a simpler du. Now we have all the information that we need to apply this formula here. And so we're saying that this equals u times v minus the integral of du times v. So what we have is the integral of x e to the x dx equals x times e to the x minus the integral of dx, or 1, times e to the x dx. So there we applied the rule. We're not done yet. You're not done until you've gotten rid of the operator of the integrand on this side of the equation. So now we actually have to integrate this, but integrating this is a heck of a lot simpler than integrating this was, and that's the integration by parts piece of it. What happened was we integrated one piece of it already, and now we have to integrate the other piece of it. And when all the integral symbols are gone from this side of the equation, you know that you are done. So this is going to become x e to the x minus, well, the integral of e to the x dx is just e to the x. Don't forget the plus c because this is the general solution. That is what the integral of x e to the x dx equals using integration by parts. Now, I would like to write a practice problem for you on here. So this is going to be practice example 1. And what I would like you to do is pause the video and work this out yourself. So you are going to find the integral of x e to the 3x dx. Go ahead and pause the video here and attempt to work this problem out. Okay, hopefully you had a chance to work that out. In the case of this problem, I would assign u to be x, and that would make du 1 dx. I would assign dv to be e to the 3x, which would make my v 1/3 e to the 3x. I can now apply the rule, and so the rule says that the integral of x to the 3x dx equals x times 1/3 e to the 3x minus is it x? Now I have to look up here, u prime. So 1 times 1/3 e to the 3x and then dx. Okay, I'm not done until I have dealt with this integral sign, until I have dealt with the integral. And so I'm going to simplify as I go. This becomes x over 3e to the 3x minus, well, the integral of this is going to become 1/9 e to the 3x plus c. And there we have it. Okay, let's try another one. Let's try one where it might be a little bit more difficult to decide what is u and what is dv. I'm actually going to try another method here as well, just to see. I've actually never tried this method. One of the other teachers said, hey, this is what I learned, and I remembered it for 8 years. So I'm going to rewrite up here that we have the integral of u times v prime equals u times v minus the integral of u prime v. Need to make my u's a little better. Okay, and so what the other teacher told me that he taught or was taught in college was to make a box, and in that box u always goes here and dv or v prime always goes here, and you take the derivative that way, you take the integral this way, and you can fill in the remainder of your box. And then the integration by parts piece of it is you make a 7. So let's see how that works. I've never done it before, so I guess this is as good a time as any, right? So example 2, we are going to find the integral of x squared ln of x dx. Okay, so we have to figure out what do we want u to be and what do we want v to be. Now, before we actually solve this problem, I have a pretty cool little mnemonic that will help you remember which way to go. So let me see if I can import this in here so that you can see it. So I'm learning this new piece of technology and it's kind of cool so far. Don't have any complaints. All right. So integration by parts, this is a cool little mnemonic for how you can choose the order of your u. So liate. So choose logs first, then inverse functions, then algebraic functions, then trig functions, then exponential functions. That's how you want to choose your u's in this order. So this is pretty cool. If you want to pause the video and write that down so that you have it, you can. So do we have a log? We do. We have ln of x, and so let's choose that for our u. So I'm going to make this little box, and we are going to put our u right in the left-hand corner, and that's ln of x. Going downward, we'll take the derivative. The derivative of ln of x is 1 over x. Now the rest would be our dv. So x squared dx, and going this direction, we are going to take the integral. So the integral of x squared dx is 1/3 x cubed. So now what we can do is we can use the information in our box to apply this formula here. And what this formula here is saying that the integral of what we're searching for is u times v minus du v. And so we can actually do this by making a 7. So u times v is right here. So u times v, so we have ln of x times 1/3 x cubed, and then du times v is going upward, and you just want to make sure you end at the point. And so when you end at the point there, this is going to be minus the integral of 1 over x times 1/3 x cubed dx. Now, of course, we're not done until we've dealt with all of our integrals. And so let's go ahead and simplify this as we go. This is going to be 1/3 x cubed ln of x minus, well, there is an x in our denominator and then 3 in our numerator. So really this becomes 1/3 x squared dx. Now this is just a simple power rule to integrate. You're going to increase by one exponent and then you'll divide by that new number. So this becomes 1/3 x cubed ln of x minus, well, I'm going to increase this to 3. I'm going to divide by 3. So this becomes 1/9 x cubed plus c. And that is our integral. So that's the integral right there. So this little mnemonic up here is pretty cool. Light. So logs, inverse, algebraic, trig, exponential. If you choose your u's in this order, normally it will make your life a little bit easier. So let me go ahead and give you a practice. So let me give you, we'll call this practice 2. And again, pause the video, work this out. So find the integral of the square root of x times ln of x dx. You do not have to use the box if you don't want to, but I do ask that you pause the video here and try to work this out. Okay, so the first thing we need to do is figure out what is u and what is dv. So what is u and what is dv? So looking down here, I would say that ln of x should be our u. And anytime you have an ln of x, you are going to want your ln of x to be your u. So I'm going to use a box. You do not have to. I think it's a cool little trick. And I'm going to say ln of x, which makes this 1 over x. My remainder, the square root of x dx, ends up being this. And then when I integrate the square root of x, I'll make a little side note right here. Square root of x is x to the 1/2. So I'm going to bump that up and divide. So when I bump that up, that becomes x, ooh, that was ugly, x to the 3/2. And when I divide by 3/2, this becomes 2 over 3. Okay, so now I can go this way. And so I'm going to have 2/3 x to the 3/2 times ln of x minus 1 over x times 2/3 x to the 3/2. And of course, that's going to be the integral of that. So simplify as we go, and this is going to become 2 over 3 x to the 3/2 ln of x minus, I have 1x here, okay, and I have 3/2 x up in the numerator, and so that ends up just being a 1/2 exponent. So I'm going to have 2/3 x to the 1/2 dx. When you integrate, you increase by 1, and then you divide by your new number. I'm running out of room. I guess I could move this up. Let's keep moving that picture with us so that we have it. So this becomes 2/3 x to the 3/2 ln of x minus 2/3 times x is going to become 3/2, so this is going to be times 2/3 because we divide by our new exponent, which makes our final answer 2/3 x to the 3/2 ln of x minus 4, oops, I clicked a button, I'm sorry, 4/9 x to the 3/2 plus c. Okay, so there we go. All right. Surprisingly, one of the most commonly used applications of integration by parts involves integrants consisting of single terms, such as the integral of ln of x dx. So by using integration of parts, we can figure out what the integral of this is. Now, looking at this mnemonic here, we want to pick our u's in this order. And so we are going to want ln of x to be our u, which means that dx is our dv. So if I were to set up this table, where's my pen at? So if I were to set up this table here, I would put ln of x here, which makes this 1/x, dx, which makes this x. Now, what this rule says is that ln of x dx integral of that equals x ln of x minus the integral of 1/x times x dx. Well, that becomes x ln of x minus the integral of dx, and the integral of dx is just x. So this is the integral of ln of x dx using integration by parts. Some integrals require repeated use of integration by parts. And so let's do an example of that right now. All right, so we're going to call this one example 3. And we want to find the integral of x squared times sine of x dx. Okay, so when we're doing this integration by parts, we have this pretty cool mnemonic over here to help us figure out what should we assign u to be in what order. So logs, inverse, algebraic, trig, or exponential. We have two possibilities for u. We either have x squared or we have sine of x. X squared is algebraic, and algebraic is before trig. And so we're going to say our u is that x squared. So let's say u is x squared, which makes du 2x dx. And if x squared is our u, then our v, our dv, has to be sine of x dx. And the integral of sine of x is negative cosine of x, because the derivative of negative cosine of x is sine of x. Okay, so now what we're going to do is we are going to do u times v. So x squared times negative cosine of x minus du times v. So the integral, and it's going to be negative 2x cosine of x dx. Now a negative and a negative makes a positive, so we can make that a positive. And remember, this is all equaling each other. So negative x squared cosine of x plus the integral of 2x cosine of x dx. Now, we are not done until we've dealt with this integral. Our answer is not going to have an integral in it. We need to find the antiderivative. Well, what I notice is I have another product here. I have 2x times cosine of x. So because I have another product, I'm going to apply the integration by parts again. So I'm going to do it again. Now, one thing to keep in mind is that if you assigned this to be u the first time, then its derivative must be u the second time. If you switch, you're going to do a circular function and you're going to get yourself back to the original. So when you're doing repeated integration by parts, make sure that whatever you had for u, its derivative is your next u. So u is going to be 2x, which makes du 2. And that leaves dv as cosine of x, which would make our v, the integral of cosine of x, is sine of x. So we're able to do this again. This piece is going to come down. It's going to come down because what we're doing is we're integrating this to try to get our full answer for this. So this piece is going to be negative x squared cosine of x. Now we're going to integrate this piece of it, and to integrate that piece, you do u times v, which is going to be plus 2x sine of x minus the integral of du times v. So 2 sine of x dx. We're not done until we've dealt with the integral. Now we don't have a product here, which is great. So because we don't have a product, we can simply integrate this. The integral of sine is negative cosine. And so our final answer is going to be negative x squared cosine of x plus 2x sine of x. And then a negative and a negative is going to make this a plus 2 cosine of x plus c. That is going to be our final answer for that question. So the integral of x squared sine x dx is negative x squared cosine of x plus 2x sine of x plus 2 cosine of x plus c. And that is when you are using the repeated, when you're doing the repeated integration by parts. So let me give you an example to try to work out. And so we'll call this practice 3. And your practice 3 is going to say find the integral of x squared e to the x dx. So what I would like you to do is pause the video here and attempt to work this problem out. Okay, hopefully you work this problem out. The first thing we need to do is identify what is our u and what is our dv. So u will be x squared, which makes du 2x. That is going to make our dv e to the x dx, making v e to the x. The integral is going to be u times v, so x squared times e to the x minus the integral of du times v, so 2x e to the x dx. We aren't done until we have dealt with the integral. Because this integral is still a product, we are going to have to do integration by parts again. But this piece is just going to get carried down with us. That piece is done. So we'll carry that one down with us, and let's go ahead and integrate by parts again. U will be 2x because you need to be consistent with your use, and du will be 2. Let me move this out of the way. Our dv, oops, sorry guys, our dv is going to be e to the x dx, making v e to the x. So we are going to multiply these two together. I'm keeping that sign with me. I don't want to mess up on that sign. 2x e to the x. This sign is staying with me, and it would be minus negative integral. So this becomes a plus the integral of 2 e to the x dx. If that was hard for you to follow those signs, this is what just happened. Let me use this little galaxy pen. Uh-oh. Uh-oh. Oh my goodness, I just had a heart attack. Whew. Okay, so what just happened was it was x squared e to the x minus the integral of 2x e to the x dx, meaning that was x squared e to the x minus 2x e to the x minus the integral of 2 e to the x dx. And then I distributed in my negative sign, making this x squared e to the x minus 2x e to the x plus minus minus the integral of 2 e to the x dx. So in case you had a hard time following the signs that I did in my head, that is what I did. Okay, so now we have to actually integrate this piece, which is awesome because we love integrating e to the x, and we get that as our final answer. All right, the last example that we're going to do is going to be insane. Your mind is going to be blown, I think. So this example, I'm not even going to give it an example number. We're going to call this a fun, crazy example. And we are going to find the integral of e to the x cosine of x dx. And what makes this so crazy is that e to the x and cosine of x are both circular, meaning they're just going to keep coming back to itself. So every time you take the derivative of e to the x, you're going to get e to the x. Every time you take the derivative of cosine of x, you're going to get negative sine of x, and then it's going to go negative cosine of x, and we're just going to do something a little crazy here. So knowing that both of these are circular, neither one of them is going to be more simple than the other. Just for fun, let's say u is e to the x and du is e to the x dx, which makes dv cosine of x and v would have to be sine of x. Now, like I said, this is going to be insane. So this is going to equal, and let me do it in another color, u times v minus du times v. Well, we didn't get very far, did we? We didn't get very far because now we have to integrate this piece, and the integral of that piece is going to it's going to be another circular function. And because we called this u in the first one, we're going to have to call it u in the second one because you have to be consistent. And so let's do it. Let's do it. It is going to be great. So let's integrate this. And so I'm just going to put that down here. We're going to integrate this. And when we integrate that, we're going to say that u is e to the x, du is e to the x. That should be a dx. Sorry, guys. Which makes dv sine of x, meaning v has to be negative cosine of x. And of course, we're going to do u times v. Negative goes out front. cosine of x. And remember, this whole thing is actually negative, right? Because of the negative in the front. So negative out front. So negative e to the x, and then we'll multiply these guys together, and we get minus negative e to the x cosine of x dx. And then, well, that's going to make a positive, right? So let's see this here. Let's see this. This turns into e to the x cosine of x minus, there's three negatives, 1, 2, 3, e to the x cosine of x dx. Whew, this is insane. So this I can actually replace with this. Well, this I can actually replace with this. So that's what I'm going to do. I'm going to erase this right here, and I'm going to replace it with what I know that it equals, because that's the way equations work. Okay. Let me write it in the galaxy color so that you know where it came from. Plus e to the x cosine of x minus e to the x cosine of x dx. Well, where did we go? Because when I try to integrate this by parts, it's going to be exactly the same thing again. Right? Because look, isn't that what we started with? Isn't that what we started with? This is insane. This is crazy. So we are going to apply all of the rules of mathematics here. Right now, we have an algebraic equation, right? We have this guy. Oh, sorry. We have this. And you know what? I am just sick of going in circles and circles and circles. So I'm going to add this piece. I'm going to add this piece to this side because it's the same thing, okay? And what I get when that happens is I get 2 integral e to the x cosine of x dx. 2 of them because I took this one here and I added it to the other side, and they were exactly the same thing apart from one being negative, one being positive. So I added them together and I got equals e to the x sine of x plus e to the x cosine of x. Now here's the deal. I want to figure out what the heck the integral of e to the x cosine of x dx is. If I just divide this by 2, I have the integral of e to the x cosine of x dx alone, and I have what it equals. And there we have it. That is some crazy, fun calculus. All right. So I'd like you guys to stay tuned for your practice problems. They'll be posted on Google Classroom. So stay tuned for your practice problems. You'll work through, and I hope this video was helpful.